Okay, now I'm going to do a problem from the test, or similar to something on the test, and I'm going to do it hopefully slow enough and carefully enough with enough explanation that you get this one. This one's the one that's probably the most important that you'll understand, and so here we go. It's worth the most points, so, and a lot of people struggled with this one, so that's why I'm going to do this. All right. I have y equals the square root of x. If I put 0 in there, the square root of 0 is 0. If I put 1 in, the square root of 1 is 1. If I put 2 in, I get the square root of 2, not as nice. Put 3 in, not as nice. If I put 4 in, the square root of 4 is 2. So I've got something that looks like this. And then I said x equal 4. X equal 4 goes this direction. Y equal 4 would go horizontal. And then it says x-axis. So I've got this region. That's the bounded region. The x-axis, square root of x, and x equal 4. And I'm saying I'm going to rotate it around x equal -1. Now, some people on the test, the sample test had y equal -2. On the test, I made it x equal 2, and some people didn't. They were just following their notes instead of thinking. X equal -1. You go to -1 in the x, and it's perpendicular line. So if this shape is rotated around the x, x equal -1, this point will come up, out, and go back in there and go back around behind, so it goes clear around like this. That's a circle coming up and a circle going back. So it's not quite right because I can't draw it, because it goes up in the air, hits here, then goes behind the paper and back up. This point, which is over 1, 2, 3, 4, 5, will be 5 on the other side. 1, 2, 3, 4, 5. It will go someplace there. Up, in the air, down, behind the paper, and back up. And this one will be right above it, 2 above it, clear over down to there. And some of you are still having trouble seeing those. If you are, let's come in, let's work on it. So this shape would go this way, this would go this way, and this one is here. So that's 2 sections of the whole thing that goes around. Okay? All right, now we need to find the volume of this using the disk method or washer. And then we have to do it again with the ring or shell method. Okay, this is the axis of rotation. When you do the disk washer method, you take a slice. And some people are not getting this slice idea. It's like if this was a loaf of cheese that went around like this, had a hole in the middle, you're taking the slicer right straight across and taking off a layer. And then the next layer and the next layer. And if I slice it someplace like this, it would be over here. Okay, my camera cut out on me, so I'm going to have to splice these together. So I was saying it was sliced this way and here, and it comes up around, so it's going to be like a washer. This would be the big radius from going around this way. So I've taken the slice and laid it down, and then there's going to be a hole inside it. So there's an inside radius, and that would be from the center line to there. And there'd be an outside radius from the center line to there. And I've labeled those. Okay? So, make sure my camera's staying on here. Now, so this is the washer method. So this is going to be a big circle, and the area of a circle is pi r squared. But we're doing a disc, so it'll have some thickness. And the thickness is important to get straight. The thickness is up and down, which is going in the y direction, so it's going to be a dy. And so the whole disc from here to here, with including the hole, would be pi r squared dy. And y, the thickness, is going to go from here up to there, which is 2. Remember, if we put 4 in, we got the square root of 4 is 2. So it would go from 0 to 2. That would be the whole washer. Then I need to remove the center. So I have to subtract. It would still be, a thickness is still dy. The hole is also a circle, so its area is pi r squared, and it's going to go, we're going to evaluate the size of the hole, which changes from a small one to a larger one as we go up to 2. So we're going to go from 0 to 2 on it also. So we have the radius of the big one and the radius of the small one. Now once again, the book said r of x, but the variable is y. So the book's formula for this one would be pi r as a function of y squared dy. It's probably better to not see that y, because a lot of people try to multiply it. And I don't want you to think that's r times y. It's r using y as the variable. So what is y? What is the radius? So the radius starts here and it goes this direction. That's in the x-axis direction, so that's going to be x. And the radius out to here is going to be x, but that radius stays the same the whole time. It stays, now this says 4, but the center is back here, so the radius is 5. So the outside radius on this one is 5. No need for a variable because it's always the same. So it's going to be 5 squared times pi, evaluated from 0 to 2, dy. So I don't need any y's in here. That radius is staying the same. Minus 0 to 2 pi. Now this is the radius for the inside. Now if I'm graphing, you go over x and up y. Over x, this is in the x direction. So this is the x value to this point. That's x. But the radius starts here and gets to there. So it's the x plus one more unit. I don't care whether this is minus or plus or whatever in terms of the graph. I see that this is x, that is x over x, but we have one more added to it. So the radius is x plus 1 squared dy. Now, remember, it's dy. This is x plus 1. It's x plus 1 because it's going in the x direction. So we have to replace this y, this x, with an expression that it's equal to in terms of y. Now if you look up here, the square root of x is y. So if I square both sides, I get y squared is equal to x. So I have to replace this x with y squared. So this part turns into the integral from 0 to 2 of pi y squared plus 1 squared, because it's radius squared, that's the radius, but with the y squared replacing the x, that's the radius, dy. Now we can make this one integral, but we can leave it as two separate ones if you want. That's not an issue. So here we go. This is just a constant. That's not a variable. That's 25 pi. The 25 pi can pull out, and so I have 25 pi. And then the integral of 1 dy would be y evaluated 0 to 2. I put in the 2, and I get 2 times this. And then I put in 0, and I get 0 times that, so I get 50 pi. That's the volume of the big disk evaluated all the way up. So that's, if this was just a complete solid, it would have a radius of 5, a height of 2. So that's what this is giving me. 5 squared, 25 times pi times a height of 2. So this one's just giving me the volume of a can that's this size, pi r squared h. I didn't even have to do an integral on that one, but I did it just to show you the calculus. But we have to subtract this, the volume in the can that would fit in here that's going around. So we have to subtract that out. That one's a little trickier, so we need to use our calculus. The pi will pull out, so we're subtracting all this, and it's going to be pi, and we're going to have y squared plus 1 quantity squared. So I'm going to have y squared plus 1 times y squared plus 1. So I'm going to get y to the 4th plus y squared plus y squared plus y squared plus 2y squared plus 1. And I still have to integrate that. I just multiplied that out. From 0 to 2 dy. The y's and the y's match up. So I can do the integration. Again, this part was just 50 pi minus, we got pi times, now we're going to do the antiderivative of y to the 4th is going to be add 1 to the power, so it's going to be y to the 5th divided by 5 plus add 1 to 2 makes 3, so it's going to have to divide by 3, so it's going to be 2 over 3 y to the 3rd and multiply by a y. And I got to evaluate that from 0 to 2. And if I put 2 in there, 2 to the 5th is 32 over 5. 2 to the 3rd is 8 times 2 is 16. And then put 2 in there, and I get plus 2. All of this minus, now put 0 in there, and I get 0 plus 0 plus 0, so I get minus nothing. And that's all times pi. So my answer is going to be 50 pi minus this many pi's. And that's just a calculator problem, and you should be able to get an answer for that. Let's see. 5 goes into 36. This is 6 2/5. This is 5 1/3. So I got 6 plus 5 plus 2, 11, 13, and plus 2/5 plus 1/3. 13, let's see, that would be 15ths. 6 and 5 is 11/15. So 6 plus 5 plus 2 is 13, and 6/15 plus 5/15, 11/15 times pi, and 50 pi minus that is 36 4/15 pi. Okay, now I'm going to do the ring method. Okay, hopefully my phone will stay on here. Keeps wanting to shut down. The ring or shell method, you don't slice perpendicular to the axis, you slice parallel to it. So I'll make a slice here. Now, if that's the slice, it's going to, and if it's following this shape, the other part of it would end up over here. It would be a piece of pipe, and I don't know if you can visualize it. If you're having trouble with this, you need to come in and we'll make some models here. But this goes out, comes around, goes back in, goes around behind. So does this, and so we get something that looks like a can, an empty can, no top or bottom, just the metal around it. Goes from here to here and behind. So we want to find the volume of that can and then the one that's just outside of it, and just kind of build it up like we're building shells all the way out. From here all the way out. Now, if I'm slicing it this way, its thickness is sideways. It's in the x direction. So its thickness would be dx, whereas slicing this way, the thickness was dy. That's why we had dy on all of those. This one has to be dx. And so now to find the volume of this piece of pipe without the hole inside, we think of the thickness, and then we think about how far around and how tall it is. I'll call this the height. I'll call the distance around 2 pi r. That's the formula for the circumference of a circle times the thickness. And that's because if I cut it open and laid it out, it would be a rectangle. A rectangular solid that's not very thick. The thickness would be dx times the height times the distance around. So the formula for the ring or shell method is 2 pi r h. This times this times this. Times dx, or times the thickness. This way it's dx. If it was something going this way around, the thickness would be a slice this way and it would be dy, but it's dx. So it's 2 pi r times the height times the thickness. And we're going to integrate that. Now what does x go from? Well, x starts here for this curve and ends there. So it would go from 0 to 4. I have to look at that to know that. So I have to know that. I have to know it from the picture. Okay. So here we go. This is saying that r, in the book, if they wrote this one, they would say r has to be a function of x, and so does h have to be a function of x. That's not times like it looks like in the book. We have to write r using x's. We have to write h using x's. So we're going to have the integral from 0 to 4 of 2 pi. What is r? Well, again, this is the axis, so how far is it over? Well, if we're going over, that's to a point on the curve, that's an x. From the x-axis over to a point on the curve, that's x. That's x. It's the variable x, but the radius is a little bit longer. Don't worry about it being minus. It's longer, so it's x plus 1 more. So the radius is x plus 1. And fortunately, it's in the right direction. We're trying to do dx, so that one is fine. R is a function of x. The height, though, is this direction. Now, if we're on the curve, this is y for on the equation. So the height is y, but we need it to be in terms of x. H as a function of x because it says dx. We need it in x. So again, we go back to our equation, and y is, it's the square root of x. So we pull out this y and we put in the square root of x. Now it's all x's. The 2 pi is a constant, so we pull it out and we get the integral from 0 to 4 of 2 pi. I can distribute the square root. I can't integrate this separate from this because they're times. That's why we do all this stuff in the last chapter. But we can distribute. This is x to the 1. This is x to the 1/2. So you add the powers, so we get x to the 3/2 plus x to the 1/2 times 1 is x to the 1/2. Now I can use the power rule. So I will get 2 pi. So if I add 1 to this, 3/2 becomes 5/2. And what we get for the new power is what we divide by or invert and multiply by, which is 2/5. Add 1 to 1/2 and I get 3/2. And so if I divide by 3/2 or invert and multiply, I get 2/3. Okay. No more dx because I did the integration. We've gotten rid of the dx by integrating, but we have to evaluate from 0 to 4. So I got to put 4 in here. So I have 2 pi. I got to put 4 in, and then I got to put 0 in. If I put 4 here, this says the square root. So the square root of 4 is 2 to the 5th is 32. So this would be 32. You can take your calculator and go 4 to the 5/2, you'll get 32. 32 times 2 is 64/5. And then if I put 4 in here, it says take the square root, so that'd be 2 cubed is 8 times 2 is 16. And then we put in zeros for both of those, and we get 0. So we get 2 pi times, let's see, 5 goes into 60, 61, 2 and 4/5, plus 3 goes in there, 5 and 1/3. So 15ths, so we get 17, and let's see, this would be 12/15 plus 5/15 is 17/15, which is, we can take 1 out of that, make 18 and 2/15. And this is times 2 pi. And 2 times 18 is 36. And 2 times 2/15 is 4/15 pi. So we get the same answer. Okay? And this one, I wanted you to do the calculus on it. Work these out, at least one of them. It's not bad to work out both of them and check your answer. Or go back here and put this into the calculator and figure out what this is and figure out what this is to make sure you get the same answer. Then work one out to show that you can get that answer using your algebra and calculus techniques.